Good morning, afternoon, and evening, Professor. Welcome to Project Fish Shield. First, a quick introduction of our members, Rui-En, Yanxi, Jimmy, Rizhe, and me, Wei Sheng. We start with the scope of this presentation and a quick overview to understand the objectives of this project, then move on to defining the problem statements before jumping into how the project works through its system diagrams and data sets, followed by individual module explanations, concluding it with our results and further explorations. The objective of our project is to develop a rule-based system that detects phishing emails that help our users avoid these forms of threats.
So starting with our project overview, phishing is a growing cybersecurity threat. In Singapore, there were close to 4,000 reported cases in the first half of 2025 alone, amounting to over $30 million in losses according to the Singapore Police Force. Among all the scam types, phishing actually ranked first in terms of case numbers, and that's where our project comes in, using a rule-based system to flag out phishing emails. PhishShield integrates 11 independent detection modules in line with these following categories. By using multiple layers of analysis, PhishShield aims to effectively identify phishing emails and protect users.
Based on the overview, we have come up with the following problem statement. Phishing emails are a growing cybersecurity threat, and identifying them manually is time-consuming and prone to error. The project aims to develop a rule-based system that can automatically detect phishing emails, helping users identify and manage potential threats more efficiently. With this, we have identified a few key challenges that our system is designed to solve. The three main challenges we aim to solve are: first, phishing emails are a growing cybersecurity threat. Second, manually identifying phishing emails is slow, inconsistent, and prone to human error. And third, is that many users lack cybersecurity awareness or tools to verify suspicious emails effectively. These are the problems that PhishShield aims to fill to be an automated, rule-based detection system that can help users identify and manage threats more effectively.
Before diving into PhishShield's detection process, let's first look at the basic structure of an email. Every email is made up of two main parts, the header and the body. The header part contains all the routing and metadata information, such as who sent it, where it came from, and the subject line. The body is the main message content, which can include text, links, and attachments. In PhishShield, our detection checks are grouped according to these two sections. Under the header, we have email authentication check, email domain check, and recipient checker. Under the body section, we will be checking for suspicious keyword or phrase detection, Unicode or obfuscation, excessive capitalization, header content, spelling error, body URL, and attachment. So overall, this slide just highlights that all our checks falls under these two main areas, the header and the body. In the following part of this video, we will be going through how each of these checks contributes to classifying an email legitimacy or potential phishing severity. Here is a high-level overview of PhishShield on how the email will flow. First, an email is received in the Gmail mailbox. PhishShield, running in the background, retrieves new message via IMAPS protocol and sends them into the processing pipeline. The pipeline then performs layer analysis header check, content body inspection, attachment scanning, and URL reputation check. All findings are then fed into the scoring engine that evaluates risk and detects hard flags. Based on the score and any hard flags, PhishShield will produce a final classification of high, medium, or low risk, which dictates the follow-up action for that message.
For this project, we used two types of dataset. The first dataset we used was from Kaggle, Spam Assassin Public Corpus, which contains a total of approximately 6,000 spam and legitimate emails. This dataset was used only during the development and testing phase to help us design and validate the rule-based features of PhishShield. After developing our detection rules with the Kaggle dataset, we tested the system using an operational dataset by retrieving emails directly from Gmail inbox via IMAP. These emails include everyday messages like OTPs, transaction alerts, and receipts. We've also included simulated test datasets from third-party testing tools to safely reproduce real-world attacks. This would ensure that PhishShield will perform accurately and reliably under practical real-time conditions. Now moving on to data preprocessing, the emails are all retrieved directly from the user's Gmail inbox and spam folders using IMAP. Each email as it is retrieved is represented as an email message object containing several structured fields such as .from, .subject, .text, .html, .attachments, and many more. So before we begin the phishing detection analysis, some steps are done. First, the sender email and domain are extracted. Then all the domains are normalized to lowercase and extra spaces are removed to ensure consistency. Next, HTML and character decoding is also done so that the content is extracted cleanly without formatting issues. after which a list of all the URLs within the email is extracted from the HTML body. And finally, attachments are retrieved and stored in memory, which will later be analyzed for potential risks.
The first step in PhishShield is to check email authentication from the email header, which ensures that incoming emails really come from the domain they claim. This is essential for preventing phishing attacks. Hence, we implemented 3 keys check. The first one is SPF, or Sender Policy Framework, verifies that the server sending the email is authorized by the domain owner. In our code, the function has SPF record, queries the domain's DNS-TXT record, and checks for the v equals SPF1 record. If it exists, the email passes SPF. Otherwise, it returns false. DKIM, or Domain Keys Identified Mail, helps confirms that an email hasn't been altered by using a digital signature. The function Gmail check DKIM rule base looks for a DKIM signature header and compares the signing domain to the sender domain. It returns true if they match and false if the header is missing or the domain don't match. Finally, Domain-Based Message Authentication, Reporting and Conformance (DMARC) defines how mail servers should handle emails that fail SPF or DKIM checks. Our function getDMARC policy queries the domain's DMARC-TXT records and returns a policy, reject, quarantine, or none. If no DMARC record exists, the function returns none. PhishShield also analyzes email headers using other several specialized functions. First, we'll have getDomain and getTLD functions, which extract the domain and top-level domain from the sender email, with special handlings for Singapore domains like .com.sg or edu.sg. Next, getMXHost function looks up the domain mail exchange servers to see which servers are authorized to send email for that domain. To detect legitimate corporate emails, reference LegicOp function check if the sender's domain matches known corporate mail host, helping distinguish organizational messages from suspicious ones. CheckEditDistant function compares the sender's domain against a list of important domains using a Levenstein distance algorithm, which calculates how many single characters edits, insertions, deletions, or substitutions that are needed to change one domain into another. If the sender domain are very similar, for example, only 1 or 2 letters are different, and the similarity ratio is above 70%, the function returns true. This check is crucial because attackers often register looks-alike domain, for example, like The checkDomainReputation function is to see if a domain is malicious, similar to checking from a dynamic blacklist. The function queries VirusTotal, which collects reports from multiple security vendors about domain involved in phishing or like blacklist. Finally, the function Gmail has many recipients check if an email is sent to a large number of recipients at one go, which can be a signal of mass phishing campaigns.
Moving on to the body analysis, both the email body and subject line will be screened for suspicious or high urgency keywords and threat patterns. These are often used as a form of social engineering technique to instill a sense of urgency or pressure the user to take hasty actions. So moving on to the code analysis segment, we start with the urgency and keyword detection. Here we actually separate the analysis for keyword and urgency patterns. So first up here will be the keyword detection for the email body. So the email body is screened for suspicious keywords commonly used in phishing. Regex here is predominantly used to match keywords in the email body to those in a predefined set of suspicious keywords. For each of the threshold of suspicious keywords that are found, the risk scoring is compounded, meaning that the more keywords detected, the more risk scoring that subsequent keywords will carry. And the total number of keywords as well as the total risk score will be returned. Similarly, for the subject line, it is also checked against our list of predefined keywords, and the total risk scoring is also returned. So moving on to the detection of urgency patterns, the body and subject are actually combined into a single text and screened for words and social engineering patterns that aim to pressure the user and force them to take some form of action. So the list of keywords actually come from 2 distinct social engineering patterns. Firstly, those that try to use time, so for example, limited time offer or immediate urgent. And this is separated into both high urgency and medium urgency patterns. The second of which would be those that aim to use fear, for example, security breach, legal actions, or fines. Again, regex is predominantly used here to match words from the combined text to those found within our predefined lists, which are up here. So the risk scoring actually depends on which list the keyword was found in. So for example, high urgency and medium urgency keywords will have different risk scoring. And the total risk score is returned after the whole combined text has been screened. Additionally, the email body will also be checked for use of text obfuscation. So the email body will be screened for use of suspicious Unicode and zero-width characters. These are commonly used to obfuscate malicious content. Additionally, the use of white text characters in the body will also be flagged, as these often provide attackers a means of hiding malicious content or padding the malicious email with gibberish to lower the overall risk scoring. So now we move on to the analysis of text obfuscation. So to start, the email body is checked for Unicode characters, so characters that are not found within the ASCII table, as these are commonly used as a method of obfuscation by attackers. So the total number of Unicode characters in the body is returned, along with the percentage of the characters as part of the whole email body. So the higher the percentage count, the higher the risk scoring will be. And then we move on to detection of white text. So the HTML content of the email body, if there are any, is checked for the presence of white text characters. So the HTML content is first passed into beautiful soup to be cleaned. This ensures that the relevant text and elements are extracted as Python objects and can therefore be worked upon and analyzed. Regex is used to detect the color styles that indicate white text. For example, the color name white, or hex values and RGB values that represent white in the various HTML elements, including inline styles, body text, and SVG graphics. So move on to the detection of zero-width characters. So a simple function here is implemented where the email body text is checked against a list of the most commonly used zero-width character codes. So the total count of zero-width characters is returned, and the risk scoring is assigned based on the total count. So now we'll move on to the combined scoring. So as you can see here, the different analysis function mentioned just now have their own individual risk scorings, and these are actually weighted as part of the combined email risk scoring. So for example, as you can see here, the white text and Unicode percentage, they both carry 15% of the overall email body scoring. So following this, the whole email body risk scoring actually constitutes 40% of the total overall risk scoring of the email.
The word analysis function is made of two modules, the excessive capitalization module and the spelling mistake module. Threat actors often fail to catch this as they may be unfamiliar with the English language, or lack the time and capability to proofread all their emails. The spelling mistake module determines the spelling error rate. This is then passed on to the scoring matrix to determine its level of suspicion. The excessive capitalization module checks for suspicious patterns of capitalization and flags it as suspicious if it exceeds a certain threshold. Now let's take a closer look at the excessive capitalization module. First, we have the raw text. The raw text is then split up into raw words. These raw words are then cleaned by only accepting words with alphabets in them or alphabets with apostrophe in them. These cleaned words are then added to a list of words. The list of words, within this list of words, we combine words with apostrophe in them to form core words. These core words are then checked for uppercase letters and lowercase letters. If they start with an uppercase letter, followed by lowercase letters, this is normal as they appear in names, locations, and addresses. A word is considered all caps if it only has uppercase letters and no lowercase letters. If a word has uppercase letters and lowercase letters, but does not start with uppercase letter, it is considered mixed. Since we have defined all of that, we're then able to find the amount of suspicious words in this email. This can be determined by adding the total amount of mixed words and the total amount of all caps. If they appear more than 20% of the time in the text of the email, we consider them suspicious, else it is not. We first import the regular expression library into our program, followed by the enchant library. The enchant library is then used to import both the US and UK dictionary. This is so that we can check our spelling against both of these dictionaries later on. We then clean our text by first normalizing the curly quotes with straight apostrophes. The curly quotes may affect our word search later on. We then use the regular expression function .sub to replace out strings that has HTTPS followed by a string or www followed by a string with a blank space. This effectively removes them. We then find all the words that have alphabets in them or alphabets followed by an apostrophe in them. This gives us our list of words. This list of words is then checked against the UK and US dictionary. If the words do not exist in either the US or UK dictionary, it is considered misspelled. With this, we are then able to determine the error rate. The error rate is simply just the amount of misspelled words divided by the amount of words. This error rate is then returned back to the scoring matrix for further evaluation.
There are a few URL-related checks in Project PhishShield. The program will first extract the URL from the email body before passing that as the argument for other analysis functions. Firstly, it will check if the URL is a homograph tag by comparing the original hostname with its ASCII representation. Homograph tags use visually similar characters to impersonate legitimate domains. It then checks if the email starts with HTTP or HTTPS, with the former being less secure. It then checks for shortened URLs in the email body and attempts to unshorten them to reveal the destination. URL shorteners are often used in phishing attacks to hide the true destination. The URL is also queried to VirusTotal to check against this database. And finally, it is classified under one of the 6 categories listed here. This function checks if a URL is a homograph tag. The function first passes the URL to extract the hostname. From there, it uses the IDNA encoding standard to convert any internationalized domain names to their ASCII equivalent. If the encoded ASCII domain differs from the original hostname, it is flagged. The function here first identifies any IP addresses in the URL using regular expressions. It then checks for suspicious TLDs against the predefined list of suspicious TLDs defined here. It then checks for the presence of multiple subdomains in the hostname, and then here it calls the previously mentioned homograph checking function to check for the presence of homograph tags. Finally, it will check for the presence of the add symbol character, which can be used in URL obfuscation. This function here checks for the presence of insecure HTTP links in the email. For each URL passed, it will check if it starts with either HTTP or HTTPS. If it starts with HTTP, it is appended to the insecure URLs list. This function unshortens a URL by following redirects. There is a predefined list of common URL shorteners stored in the shorteners variable. The function will first check the URL against the list, then use the request.hit module to follow redirects to get the final URL. Once the shortened URL has been found, the program will do the previous checks against it, such as suspicious TLDs, presence of IP addresses, etc. This is used to check the URL against the VirusTotal database. It encodes the URL in a required VirusTotal format and then sends it as a request using its API. VirusTotal will return whether the email is malicious or not. So this is the main function that does the URL checks. It first extracts all the URLs from the email body using regular expressions. From there, it will proceed to call the other functions in the Python file and pass the relevant information such as the extracted URLs as the arguments. Finally, each of the URLs analyzed are categorized under the 6 category lists here. Here, the categorized URLs are converted into sets and returned back to the main program file. Here, the length of the category's basic suspicious characteristics, shortened URLs, and insecure links are multiplied by a defined number and added to the overall URL risk score. The URL risk score is taken into account in the final combined risk score for the email. It has an overall weightage of 25%. However, if the URL is detected to be malicious from VirusTotal or has homograph attack traits, it is automatically categorized as a high-risk email.
Moving on to the attachment analysis, the program flags out attachment that contains suspicious extensions such as executable files. It also checks for misleading double extension, which makes a file seem safe while actually being an executable. It will also iterate through files within zip archives, as phishing campaigns often use zip files to bypass email filters. Each file hash is then queried to an external API, VirusTotal, to determine if the file has been flagged or matches any known malware signatures. This VirusTotal check improves the overall detection accuracy by limiting false positives. First, looking into attachments PY, there are 2 predefined lists and 2 main functions that check for attachment extensions. The 2 lists are for suspicious extensions and valid extensions. File contains suspicious extension checks if the extension of a given file is within the suspicious list. It returns true if it is within, else false. File contains wrong extension checks if a given file name has double extensions, with the last extension being in the suspicious list and the second last extension in the valid list. It returns true if it is both within, else false. Now looking into hashlookup.py, there are also two main functions. Is hash suspicious will compute a given file's hash and queries it against the VirusTotal API. It will return a dictionary containing file hash and number of antivirus engines that has flagged it. Inspect zip and check content will inspect the contents of a zip archive in memory and check each file for suspicious characteristics. It returns a list of dictionaries with each dictionary representing details of each member from a zip file.
Here is a demo of our whole entire program integrating with Gmail. See on the left side of the screen is where we start our Project PhishShield in the background by running Python Gmail main py. So as Project PhishShield is running in the background, it will actually fetch latest emails from the Gmail mailbox. As you can see, once it fetches the Gmail mailbox, it starts the analysis progress as printed in the terminal. Once the process is done, it will then classify the email based on high risk, medium risk, and low risk. And the results are as shown above. The PhishShield program authenticates to Gmail over IMAP by reading the email address and add password from an env file. The program starts looping through two main folders, the inbox and spam folders, which are defined in our configuration. From there, it fetches any unread emails up to the limit we set without marking them as read. This makes sure we only process new email while keeping the user's mailbox unchanged. To avoid duplicate processing, every email's unique ID, known as UID, is stored in the set called processUID. So if the same email appears again, the script will automatically skip it. Once the new email is detected, the script calls the analyze email function. This is the core analysis engine defined in the Gmail scoring matrix, where it checks the email's header, body, attachment, and URLs and returns several detailed results. Let's dive deeper into it. This function, analyze email, performs a full phishing risk assessment by combining results from header analysis, body analysis, attachment analysis, URL and subject keyword analysis. When the email message is passed into this function, it will first analyze the header in the analyze email header function. The purpose of this function is to analyze the email header to detect sender-related risk and verify authenticity. It helps to identify whether an email is from a legitimate source or if it's showing phishing indicators such as fake domains, missing authentication, or suspicious patterns. The function first extracts key information about the sender to help them to understand where the email originated from. Moving on, we have the whitelist checks, where it checks the sender domain is recognized, safe, or suspicious. Next, we also have MX record and authentication check. This is to validate whether the domain has a proper email configuration. It also checks the sender reputation and whether it mimics a trusted domain. Here is the scoring logic, where each suspicious factor increases the risk score for the header section only. A higher score means the more red flags in the email header section, where legitimate or corporate domains get lower risk adjustment. Then, based on the score assigned to the header, it will assign a risk category for the header category only.
Now in the analyze email body, the program will first extract the plain text and HTML content from the email message. Using this content, the various check for obfuscation, spelling, and excessive capitalization is done, followed by the urgent pattern analysis in the body. After which, URL checks are also done, and the URL scores are then calculated based on the number of URLs in each category. Body scores are then calculated based on the above results, and then all the scores will be returned with the results. Back to analyze email, an urgency pattern analysis is then done on the subject line and given a higher score than the urgency pattern analysis done within the email body. Moving on, the program now does the attachment checks within analyze email attachments. Within analyze email attachments, it iterates over each attachment in the email and only checks if it is an actual attachment or inline attachment like an embedded image. If it is a zip file, it will call the inspect_zip function and append each of its results into the file's detail list. Else, it will just do the VirusTotal API query and the extension checks. The results will then be appended into the file detail list as well. Once done, it will return the full file detail list. Back to analyze email, all the scores are then combined and weighted. There will be hard flags such as having homograph URLs being flagged by VirusTotal, edit distance being suspicious, or having blacklisted domain IP. If the email contains hard flags, the results are immediately returned with high-risk category and a combined score of 100. Medium risk adjustments are also done if the email contains insecure HTTP links or suspicious attachment extensions. Categories are then assigned based on the combined score, and results are then returned to monitor Gmail.
Here are some of the project results, and this is a high-risk example. So look at this email. It looks harmless, right? Just a picture of a cat and that's nothing much. However, this email is classified as high risk as it contains malicious and insecure URLs, including links flagged by VirusTotal. All these URLs are actually embedded in the image itself. And there is also a suspicious attachment with a dangerous PY extension attached to this email. Hence, these indicators strongly suggest this is a potential phishing email. We also have a medium risk project result, where this email is classified as medium risk since it has a suspicious attachment with a risky file extension. And several warnings indicators in the body such as excessive caps and multiple suspicious phrases, even though SPF and DKIM have passed. Last but not least, we have a project result on low risk, where this email is marked as safe because it contains no suspicious phrases, malicious link, or risky attachment. The only attachment is a clean image file, and both SPF and DKIM authentication check pass successfully.
After this current implementation of Project PhishShield, there are a few future considerations that can be implemented for the project. While the current rule-based approach provides effective detection of known phishing patterns, it may have difficulties detecting more sophisticated phishing techniques. This is where the possibility of machine learning and AI features would be considered. There are two aspects which could be considered. Behavioral analysis can be used to train models to detect linguistic and social engineering patterns beyond rule thresholds. Anomaly detection can be used to apply unsupervised learning to flag emails deviating from a user's normal communication style. In addition, Project PhishShield currently runs from the VS Code terminal. To improve user accessibility, a simple website front-end can be created to display the results with a dashboard interface. A prototype may be built using low-code tools such as V0, Bolt, or Lovable before implementation using HTML, CSS, and JavaScript.
Aside from the current detection categories, several additional methods could improve our accuracy and capabilities. These include geolocation checks that flag an email if its IP and domain origin is from a different location, a sandbox that allows our users to safely inspect their contents, multilingual support, extending our detection range beyond the English language. Furthermore, we could also extend our analysis to go beyond Gmail and support other IMAP providers such as Outlook and Yahoo.
So to round it off, our Project PhishShield addresses the growing challenge of phishing by automating detection across 11 key categories, covering header authentication, email body content, URLs, and attachments. By combining rule-based heuristics with external validation through VirusTotal, the system accurately flags malicious emails while reducing false positives. We tested it using both pre-labeled datasets and simulated operational emails, showing that it can process diverse email types effectively. PhishShield is designed to be a lightweight and practical for real-world use, and it also provides a strong foundation for future enhancements, such as machine learning integration, broader IMAP support, and a more user-friendly interface. That will be all for our project demonstration. Thank you.